Hello friends, this is part 4 of physics honors paper electricity and magnetism. This is solution of this paper electricity and magnetism of Guwahati University 2022 second semester. And here you see I have already made part 1, part 2 and part 3, and links are given in the description box. So this is part 4. So before we start, let me tell you that if you are new to my channel, and then please subscribe the channel and share with your friends if you think these videos are helpful, and hit the thumbs up button as well. And if you want me to help you creating contents for your higher semesters as well, please subscribe the channel. And if you want any other course, you can find a mathematical physics course in my channel. If you just go to the playlist, and you may check there. And after solving this paper, I'm gonna create contents on electromagnetic theory also. That means this electricity and magnetism paper also. So just stay connected. Okay, I will create a separate playlist for this paper. Okay, so now let's start. So this is question number 3E, right? So first three questions, four questions of question number 3 we have already solved in the previous part, 3A, B, C, D, right? So links are given in the description box. If you want to watch them, you may go through. So now here is the question. So that a small current loop equivalent to magnetic dipole. So here is the current loop. You can see this blue color loop is the current loop. Here I current is being followed through this coil, this loop. Then if you apply the right hand thumb rule, then you will get, here you see this red color circles are nothing but magnetic field lines that will be directed as shown in this figure, right? And through the center the direction will be like this, direction of magnetic field will be like this. So how to apply the right hand thumb rule? Now you see, if you point the thumb towards the direction, in the direction of current, and the remaining fingers will warp around the conductor in the direction of the magnetic field, right? That's how we determine the. So here you see, this is the thumb of your right hand, and the remaining fingers are supposed warp in this direction. Then this is the direction of the magnetic field. So hope you have understood this. It's in this diagram it is not possible to draw that for me, so that's why I couldn't show that here. I hope that you can imagine that things. Okay, you can apply yourself the right hand thumb rule. So we know then, in case of magnet, if you compare this with a magnet, then you see, we know that magnetic field lines emerge from north outside the magnet and merge at south. So that's why this side will act as a north pole, and this side will act as south pole, right? So what will be the dipole of this? And we have considered that area of this loop, this area is A, capital A, we have considered, right? And how to calculate the dipole, magnetic dipole of this loop? So its magnetic dipole will be equivalent to a magnetic dipole to the magnetic dipole of a magnet, of a bar magnet, whose electric field is identical to this, right? So that's how we can calculate. Now you see, as I have written, if we have a bar magnet having exactly same kind of magnetic field as shown in the figure 2, this is figure 2, right? Figure 2. Then dipole moment of the loop is equivalent to the bar magnet, that of bar magnet. That means magnetic dipole of this bar magnet. So now you see magnetic dipole moment of the loop M, that gonna be directly proportional to I, because increase in current that gonna increase the magnetic field strength around it, and it is also directly proportional to the area of cross section. And combining these two, we can write this, right? And if you want to write equal sign, there will be a constant. In SI system, the value of this constant K is 1, and that's how we have got M is equal to IA. This is the magnetic dipole. And if there are n number of turns in the coil, then it's given by n into IA, right? So in the vector form, you can write M vector. N is the number of turns in the coil, and I is the current, A is the area, right? So hope you have understood this. Now let's move on to next question. Here is the next question. So derive an expression for electric potential at any point due to an electric dipole. So here you see I have taken an electric dipole consisting charge minus q and plus q, minus q at B and plus q at A, right? So we have to calculate the potential at this point P, right? And which is r distance apart from the center of the pole, right? This is r distance apart from the center of this dipole, right? This is O. And we know the direction of magnetic dipole moment. Here you see direction of dipole moment is from negative to positive, right? That's why this is the direction of dipole moment, which is represented by P vector, right? And R vector is the position vector of position vector of the point P. This is the point P. Okay, don't be confused with the point and the dipole moment P vector, right? Now you see we have considered that these two charges, plus q and minus q, are separated by twice a distance, very small distance, twice a. And we have taken this P point is R2 distance apart from the point A, and R1 distance apart from point B, right? So here I have mentioned already, right? So the angle between the dipole moment and the position vector R, this is the position vector R, and the dipole moment P, this angle is, suppose we have taken theta, this angle is, we have taken theta. So hope you have understood this. Let me clean this picture, right? Okay, just let's have a clean view so that I can explain again, right? So here you see now you see, and I have drawn two perpendiculars from A and B respectively to the line drawn from P. So drawn from P through the O, that is O is the center of the dipole, right? So these are the two perpendiculars I have drawn, right? So if this angle is theta, then this must be also theta, right? So now you see, so we know in a dipole moment, electric dipole, these two charges are very close, right? So if I draw them very close, actually we can't even draw the figure. How we can't even show the separation, exact separation, how small it is in this diagram, right? So just I have drawn this one here, this one here, doesn't mean that they are this much distance apart from each other, right? So these two, in this case, these two angles are very small, right? As the separation between two charges of dipole is very small, that's why these two angles are very small. So that's why you see the length, you see, you can consider in that case PA is equal to PM, right? So the difference between these two sides, length of the difference, differences between the lengths of these two sides, PM and PA, is negligible. So you can neglect, right? And similarly, you can neglect the difference between PN and PB, right? So you can consider PN and PB are of equal length, right? Here I have mentioned these two. Okay, for very small these two angles, right? So hope you have understood this. Now so let me explain how. Suppose you have a right angle here. This is a right angle, right? This is the right angle. If this angle is very small, then this side will be so close to this side like this, right? Then the difference between the lengths of these two sides, that will be negligible, right? You can assume that way. So now let's move on to next page. Here you can see we have taken this triangle AMO, this triangle. Just let's check. So here you see, as I have taken the separation between the two charges is twice A, and O is the center here, so this length is A, this length is also A. So hope you have understood this. So now you see, so this side is A of this triangle. I have drawn this triangle here, right? So this side is A, and this is opposite to the right angle. That's why we can say it is hypotenuse of this triangle, and this is angle theta. That means this one, right? This angle is theta. So with the help of trigonometry, you see cos theta will be equal to, so base by hypotenuse, that is OM by A. So where from where we can obtain MO, that is equal to A cos theta if you simplify this equation. And similarly from this triangle BON means this one, this triangle BON. So here this is the right angle, hypotenuse is this, right? BO is the hypotenuse and its length is also A. So here with respect to this angle, we can take this as a base and this one is perpendicular. So with the help of trigonometry, now you see ON, we will get A cos theta. And now you see R1, the side R1, right? If you see the diagram, this is PB, this is R1, right? This R1 is equal to, here you see, this is the suppose origin, midpoint of the dipole O. This is R, right? And this is the point N, right? So here I have already told you that for this very small angle, these two sides are almost equal, right? So that's why this R1 can be written as sum of these two segments, right? So that means R plus these segments ON, we have got A cos theta, right? So that's why R cos A cos theta. And similarly from the triangle, let me clean this. Now you see from this triangle, here you see this R2. I have also told you that suppose this is P, this is A, this is A, this is the perpendicular AM. So I have already told you that for very small angle, this angle, these two sides will be almost equal. So this is R and this is R2, and here you see this length, this is suppose O, this length OM, we have already got that it is also A cos theta, and this R2 is equal to, this R2 is equal to, so here if this is O, this R length is not that one. So from here you can see from this P point to O, distance is R1, sorry, not R1, R only, right? This length PO is R here. So that's why now you see, as I have told, PM is almost equal to PA. That's why this length up from P to M, that will be R minus OM, and OM R minus OM. OM we have got here, you can see OM is A cos theta. So that's why R2 is equal to R minus A cos theta we have got. So hope you have understood this. Now potential at P due to positive charge is given by this formula. So here R2 is replaced by this value here, and similarly potential due to minus Q is given by this expression, because here we are supposed to put R1, but R1 is replaced by this value, right? So hope you have understood this. So net potential P due to the dipole, that will be Vr2 plus Vr1. Adding these two, we have got this result. So hope you have understood this. This is the result we have got. Now from here you can see we have taken LCM. Then this Q 4 pi epsilon naught, this part is same, so we have taken common, and then we have taken LCM. Doing so, we have got this. So here this is positive part, this is negative part, cancel, right? So there is minus. There was also minus cos a cos theta, but as there is minus, so minus minus plus, right? So hope you know this simplification, being a student of science. So this, because of this minus, so here you can see this sign will be plus, minus minus plus. So hope these kind of things I don't think I should explain. So here we have got this result. Now you see a is very small, so a square cos square theta can be neglected. This part is neglected because a is very very small, right? So hope you have understood this. Now if so, then V of R, that is potential at P, can be written this way, and the dipole moment P is given by Q dot twice A. So that's why Q dot twice A is replaced by P, dipole moment P, right? So in vector form you can write P dot P vector dot R cap. So that means dot product of these two vectors is nothing but P R cos theta. Let me write it correctly. Okay, that should be P R cos theta, P R cos theta, and here as the R cap is unit vector, so its magnitude will be 1, so that's why it's going to be P cos theta, as we have here, right? So hope you have understood this. So this is the vector form. So now let's go to next question. So here is the next question. Find out the vector potential at a point near a straight conductor carrying current. So we have taken a conductor. This is the conductor. Here you can see, let me draw in red. This is the conductor I have taken. This point is suppose x1, this point is suppose x2 from the origin O, and this point P is apart is at a distance of s from the origin O, and I have taken the conductor along x-axis, and P is the distance from a very small element, current element. I have assumed very small current element dl, right? And this is very small current element, so you can consider as a point. So up to that point we have taken the distance from the origin to that point is suppose x. So that's why this is x, this is s, so this is gonna be, if you use the Pythagoras theorem, that's gonna be s square plus x square, right? So that's how we have got this. This is the R, right? Now you can see the potential due to this straight conductor will be given by this formula, right? So here we have dl, so L is the length of the wire. So now you see, we know current is a scalar quantity, but we can assume, let me assume as a vector, so that I can write I x cap, because the conductor is in is along x direction we have taken. So we can replace dl by dx, right? So dl is replaced by dx, and r is equal to root over s square plus x square. So equation number 1 reduced to this form, right? So now you see, let me take out the constant terms outside the integral, right? So I have taken the constants outside the integrals. So here x cap is unit vector. Let me take this one also outside the integral here. So we have got this. So we know integration of dx by root over x square plus a square is equal to log of x plus root over x square plus a square. So instead of x we have, instead of a we have s square here, so same thing. So using this formula or this standard integral results, so we have got this result. Now here you see we have to integrate from x1 to x2 because this is the first point, initial point of the, this is one end of the wire and this is the next end, right? So we are integrating it from x1 to x2. So if you put the limits, then you will get this. Now if you use the property of log, that log m minus log n, that is equal to log m divided by n, then you will get this result. And the direction of the vector potential is will be same as the current because we have taken the wire along x-axis and we have here x cap. So this is vector potential. So direction is same as that of current. So hope you have understood. This is the next question. Obtain an expression for torque acting on a rectangular current loop in a uniform magnetic field. So this is the uniform magnetic field. This is B and this is the coil I have taken here, you can see clearly. And so when you keep a coil in a magnetic field, and this is current carrying coil, that is I here we have taken. And now you see this dot symbol, this symbol represents forces upward and this cross symbol represents forces downward, right? And here you see this dotted line represents a normal which is perpendicular to the plane of this coil, right? And this dotted line at any instant, suppose it makes angle theta with magnetic field B, right? We have taken that way. Now you see, if you take this length is B, right? You take this length is B, then this is B sine theta, right? This is B sine theta. Okay, now let me tell you, length of these two arms are L and these two sides B. Okay, so this is B, right? Okay, now here you see this is F2 force, it is acting downward and this is acting upward, and these two are equal in magnitude. Okay, so due to the opposite in direction there will be a turning effect, and that is we used to say torque, right? The torque acting on this, we have to calculate the torque acting on this coil, right? So here you see, let's go to next page. Here you see the each side of the rectangular current loop experiences a force in magnetic field given by F is equal to I is the current, right? L vector cross B vector, right? The vertical sides PQ and RS are always perpendicular to the field B. Therefore, the magnitude of the forces F1 and F2 on these sides are given by F1 is equal to F2 is equal to IBL. So here you see these two arms PQ and RS, these two are always perpendicular to the direction of magnetic field, right? So you can see that so as we have got F1 is small I L cross B, so cross product, so it can be written as I LB sine theta. Here theta is 90 degree in this case because these two are always perpendicular, right, to the field. So sine 90 is 1, that is why we have got F1 and F2 is equal to IBL, right? This is F1 and F2 is equal to IBL. So hope you have understood this. You see, by Fleming left hand rule, F1 and F2 are perpendicular to the page directed downward and upward respectively, right? So in order to know the direction of F1 and F2, those can be determined by Fleming left hand rule. Hope you know this rule because you have already got in class 10, right? Class 10 science. So I don't think I need to explain this again. And equal and parallel and opposite forces F1 and F2 have different lines of actions. So here you see, this is the line. One force is acting in this direction, another in this direction. There, like line of actions. Here you can see line of actions are parallel and they are different, not in the same line. So that's why there will be a turning effect. Okay. So I have already mentioned here that this dot symbol represents upward and this cross represents downward in this figure. This is the cross, this is the dot. Up and down are written in the figure. So forces F1 and F2 on them are also shown in the figure here clearly, right? So now you see torque is equal to force F1. Either F1 you can take or F2. Both are equal in magnitude into perpendicular distance, right? So here the perpendicular distance that's gonna be b sine theta. That means, let me explain how. So here you see, so this force F2 is acting in this direction, right? And the perpendicular distance from this line of action, from this line, is b sine theta. That's why they are talking about this perpendicular distance. That's why torque is given by force F1, either F1 or F2, because both are equal in magnitude. I have already shown here, right? So that is IBL, right? IBL. So that's why torque is given by IBL into b sine theta, right? So here you see L into B is nothing but A, that is area of the loop. This area is nothing but A, right? So you can write instead of L and B, you can replace it by capital A. This represents the area of the loop, right? And this is the required result. So hope you have understood this. Remaining questions will be solved in the next video. See you in the next video. And if you like my video, then hit the thumbs up button. Also hit the bell icon so that when new video will be uploaded, you get notified, right? So thank you for watching. See you in the next video.